Okay, fellas, right on the topic, center of gravity. Okay, so what is center of gravity? The center of gravity of an object is the point at which its entire weight is considered to be concentrated. Now, last week we studied center of mass. Center of mass of an object is the point where we can consider the entire mass is concentrated. So mass and weight, those are two things, right? Mass and weight, those are two things. Okay, so mass is the substance, the amount of substance, right? Like how much of quantity is there. But weight is depends on the gravitation field. Since Earth has gravitational attraction of around gravitation field strength around 10 Newton per kilogram. So the weight we can simply take by mass multiplied by 10, right? So if you go to the moon, the mass weight of the object will be different, right? But the mass will be same. If you take an object, for example, apple, the apple has same mass in Earth as well as in moon, but the weight is different because Earth has a higher gravitation field strength than the moon. So therefore, the weight in the moon will be different. Okay. Okay. So the definition for center of mass is or as the conceptual idea of center of mass is, it is the point where we can consider the whole mass is concentrated. Okay, so the center of gravity means it is the point where we can consider the whole weight is concentrated. Okay, so the center of gravity of an object is the point which the entire weight, so you have to highlight the term weight, is considered to be concentrated. Okay, if an object is supported as its center of gravity, it will remain perfectly balanced. Now, for example, okay, I'll take this. Now, this one has a center of gravity. Okay, if I try to balance from this point, I can't balance, but I can balance it from the middle because the center of gravity will be at the middle. Okay, right. So, if an object is supported at its center of gravity, it will remain perfectly balanced. Okay. All right. So the center of gravity is the of an object is the point where we can think the whole weight is concentrated. But that is not the actual definition. The definition we can give for the center of gravity is the point at which the weight of the object is acting. Okay. Now here, the point at which the whole weight of a body acts, irrespective of its orientation. It is also the point where the total moment of gravitation force on the body is zero. Right now, if I consider from the center of gravity, the movement to the clockwise direction and movement to the anti-clockwise direction, they cancel off. So the movement about the center of gravity will be zero. Okay. Okay. So the definition for center of gravity is that the point at which the whole weight of a body acts. Okay. So that one I can explain you like with this. I'll take a picture to show. So if you take an object, uh, material, it made of enormous number of small particles. Each particle experience gravitation attraction force, right? So they all vertically downward because the gravitation attraction is uh, acting towards the center of the earth. Okay, so they are all vertically downward. So you can see these are now bunch of parallel forces. So each weights are forces, right? So we can find the resultant of these forces. Now remember, in the moment of force, we studied how to find the line of action of two parallel forces. So likewise, now you can find the line of action of the resultant of all of these forces. So it will be acting from a particular point. It will be the center of gravity. Okay. So let's write down. So first you had to write the center of gravity of an object is a point which at which its entire weight is considered to be concentrated, and the definition is the point at which the whole weight of a body acts. Okay, the point which the weight is acting. So then we can write down. So you can draw a picture like this. First, after writing the definition, draw a picture like this. Yeah, sure. The point at which the whole weight of a body acts. Okay. So then we can write, yeah, every object is made of enormous number of small particles. Every force vertically downwards. Okay, write down. Every object is made of enormous number of small particles. These small particles experience gravitational attraction force vertically downwards. These small particles experience gravitational attraction force vertically downwards. And all of these forces are parallel to each other. And all of these forces are parallel to each other. If we calculated the resultant of these forces, we calculated the resultant of these forces, it will act from a certain point. It will act from a certain point. This point is known as the center of gravity. So if you take an object, it's made of tiny particles, right? Made of enormous number of particles. Okay, you can divide into small particles. Each of these particles weight is acting vertically downward. So all of these are parallel forces acting vertically downward. And then if you find the resultant of that, these forces, these large number of forces, if you find the resultant of this large number of forces, that resultant will act from a certain point. That point is known as the center of gravity. Okay, I'll read again. Or else I better I read and write. Okay, so every object experience, every object made of, every object is made of enormous number of small particles. I can't write this. Okay, I'll read again. Quickly note down. Every object is made of enormous number of small particles. These particles experience gravitation attraction force vertically downwards. Gravitation attraction force vertically downward. And all of these forces are parallel to each other. And all of these forces are parallel to each other. If we calculate the resultant of these forces, it will act from a certain point. This point is known as center of gravity. And this point is known as center of gravity. And this point is known as center of gravity. Okay. So the difference between center of mass and center of gravity. Okay, I'll go through this. Okay, and you can parallelly write the note. If you miss to write, don't worry, I will share the PDF to you all. Okay, so you can later on you can complete the note. The important thing is you have to understand. Okay, you have to understand the concept, each and everything. Understanding is very important. I find it's okay even without writing the notes, unless if you understand the concepts 100% perfectly. Okay. Okay, so the difference between center of mass and center of gravity, the point which its entire mass is considered to be concentrated. So we can consider the entire mass is concentrated is the center of mass. The point where the gravitational force acts on the body. Now, for example, if you take this object, we can mark its weight acting from the center of gravity. Okay, because it is that from that point only the resultant weight of the body is acting downwards. Center of mass, it is independent of gravity. It is independent of gravity or gravitation field. Okay. And it will be the same if you take a particular object, it will be the same everywhere. Okay. But center of gravity, it depends on the gravitation field. Okay. It depends on the gravitation field. Center of mass exists for all objects, even in zero gravity. Okay. So it does not exist in zero gravity environment. Okay. Because in order to act a weight, there should be a gravitational field. Okay. A meter stick's center of mass is at its midpoint. The center of gravity of the same stick changes if it's in a non-uniform gravitational field. Okay. The center of gravity of the same stick changes if it's in a non-uniform gravitational field. Okay, by the way, here in our syllabus, we discuss the center of gravity of uniform gravitation field. We don't discuss the center of gravity in a non-uniform gravitation field because it will be very difficult to do because we had to use integration and all stuff. So, and in fact, even if you go to university also, you don't much study about non-uniform gravitation field. So we studied the center of gravity in uniform gravitation field, where uniform means in the field, everywhere has the same value, right? Now, for example, the gravitation field intensity, which is we write as gravitational acceleration, the letter simple G. In Earth, roughly it is 9.81 meters per second square, but we take roughly approximately 10 meters per second square. Okay, but even this is 9.81, this value will change, no? Because if you go to altitude somewhere like Pidrutalagala, it will have a less value. G is equals to 9 point something like 7, for example, let's say 7 meters per second square. If I'm correct, when I'm studying at Peradeniya, we take as 9.6 there. I forgot, but something around 9.64 something. That range only will get, because when you go higher and higher, the gravitation field intensity decreases, because you will study in the gravitation field unit. The G is given by Gm over R, Gm over R squared. So if the distance R is measured from the center of the planet, so if you go far and far, the R increases, G decreases. But anyway, here we don't discuss about these things. Here in this lesson, we consider uh, uniform gravitation field. Okay, throughout our syllabus, we consider uniform gravitation field, which means uniform means every point in the field has the same value. That means now, for example, if I say 9.81, that will be the same value everywhere. Okay. If you want to understand how the center of gravity changes in non-uniform gravitational field, I can share you a video after this session. Okay. So, which is I have did for like a couple of years ago. That is also for one class actually. But anyway, I think it is, if I want to explain, it will take more time. So I don't want to allocate that time in this class. But if you want, I'll share in the group. Anyway, after the session, I'll share in the group. So those who want can go through that time. But if you go through that, you'll get some good idea about it. I prefer you go through that. Okay. So those are the major difference of center of mass and center of gravity. Okay, so the concepts of center of gravity, the weight of an object can be considered. I mean, so far what we discussed is a summary of things there. Same thing only I'm saying here. The weight of an object can be considered to act through its center of gravity. The weight of object acts from the center of gravity. In uniform gravity, the center of gravity coincides with, now you have to highlight this. You have to highlight this. In uniform gravity, the center of gravity coincides with the center of mass. Okay. In uniform gravitation field, I think it better you write with uniform gravity. Gravity or gravitation field both have the same meaning, but still better to go with the term gravitational field. Okay. In uniform gravitation field, the center of gravity coincides with center of mass. Okay. So that's that line you highlight and write. In uniform gravitational field, the center of gravity coincides with center of mass. Okay. Now, if I take an object like this, okay, if I take an object like this, okay, so this object has a center of mass. It has a center of mass. Now, for example, I'll draw here on the screen. So let's say I have object. Okay, so here I have object, some mass, total mass, let's say capital M. So I can consider its center of mass here. That means I can consider this total mass is compacted at this point. Okay, and let's say this is the ground. And let's say here bottom, the gravitation field is something like 9.81 meters per second square. But if you go higher somewhere here, the value is something like less 9. Let's say 9.5, for example, meters per second square. By the way, these values are exaggeration, because if you consider like 1 centimeter, for example, 10 centimeter object, or even 1 meter object, there wouldn't be this much of considerable change in the gravitational field. the change will be very small, like in 0.00 and like in the fifth decimal place, right? So there will be a small change and it's negligible. So therefore, we can consider our normal field is uniform gravitational field, because the change in small distances, even 1 kilometer also have like 1 decimal place in change. So therefore, still we can consider as uh, uniform field. I mean, our atmosphere we can consider as uniform field. But suppose now let's say this object I have drawn in the screen, its center of mass is I have marked here, and if the field is not uniform, that means if you go higher and higher, the field is changing, means then the center of gravity will not be on the will not on the center of mass, it will be different. Now here bottom the field is high, therefore it could come somewhere here. So center of cm could be here, cg center of gravity will be somewhere here in non-uniform gravitational field. But if the field is uniform, then center of mass and center of gravity will coincide. Okay, that is very important. Okay, and if the shape and the density of object are uniform, that means the density is uniform, density of the object is uniform, the center of mass will be at the geometric center. Now, for example, let's say you have a rod. You have a rod. Okay, let's say you have a rod length, let's say 10 meter. Okay, and if the rod is uniform, if it's uniform, that means mass is distributed uniformly, homogeneously everywhere on the rod. Therefore, if you do the calculations, like the center of gravity, how do we find the center of mass? Center of mass, let's say RCM, is we find using sigma mi xi, the total movement divided by the total mass, sigma mi. So if you do that calculation, you will get the center of mass is here. Okay, cm, center of mass will be here if the object is uniform. Okay, but if it's not uniform, let's say it is non-uniform, this much is much denser and this much is lighter, then the center of mass will be deviated from its midpoint to somewhere here. Do you all understand? Do you have any questions from the discussion so far? Sri Lanka has the lowest gradation intensity from Earth, right? I'm not sure, but I have no idea about it. If you have any resources, you can share it to me so I can go through that. By the way, I think the largest gravitation field is present in Jamaica, right? The largest gravitation field is present in Jamaica. Also, I think you may have heard of Bermuda Triangle, where the flights and all disappear. So it is what do you call, Abiras at a mystery. It's a like Area 51. The Bermuda Triangle also biggest mystery those days. When I was used to using as I mean first time I read about Bermuda Triangle in Vijaya paper, in scholarship and all. I used to read Vijaya paper, so it's a good magazine for kids. So this Bermuda Triangle is a one of the mysteries, and then the scientist has discovered that in the Bermuda region, the gravitational field intensity is so high. That's why planes and all pulled and crashes into the sea. Something like explanations are there. And also, I can give you another example about that. I told you it's closer to Jamaica. And if you consider the athletes in Olympic, the like 100 meter, 200 meter, those people who are like having gold medal, silver medal, almost from that Jamaica and related. Now, in especially if you take Usain Bolt, Asafa Powell, Usain Bolt from Jamaica, because they have large gravitational field strength, so they are walking. They experience larger weight, right? So they walk through with that weight. So if they climbing a mountain or steps, they had to carry, they experience larger weight than us. Okay, they feel larger force. So therefore, if these those people go to other region of the earth, they feel it's little bit easier for them. So that is why these Jamaica and nearby area athletes are performing more well in these races and all. Okay. Okay. Some say Sri Lanka is the best place to swim, but because of low gravitational intensity and therefore less fuel burn. Might be true. I think you have sent me a link. If possible, send it through WhatsApp because, or else you can send it to TKI. So then I can access through here, so others also can uh, view it. The lowest gravity on the planet is found at the southern tip of Sri Lanka. Abhishani has shared this screenshot to me. So I'm reading that. The lowest gravity on the planet is found at the southern tip of Sri Lanka, according to NASA. Scientists have recently discovered the reason why travelers to Sri Lanka are lighter, whereas you will gain weight in Turkey. It's not be baklava. Okay. So that means Sri Lanka has less gravitational field, so therefore sending rockets from Sri Lanka would be less cheap than, I mean, not cheap, I mean, it's relatively cheap than other countries. So I hope one of my students, I mean, maybe you all can become pioneers in space and start a space exploring company in Sri Lanka, inshallah. But is there anyone who has such goals? Okay. And thank you, Hiroshi and Yavishani, for sharing this information. Wow, that's so great. Okay, so if you start a spaceship company like that, then uh, what can I say? Okay, you should take me to space, okay? Free of charge. Okay, all right. And I also have a dream of going to space. I'm serious. Anyone can think me crazy, but it doesn't matter. But I'm serious. I also have a dream to go to space, hopefully one day. All right. So determining the center of gravity. Okay. So here we have to emphasize these three concepts. First, the center of mass coincide with center of geometry of a regular shaped object if the mass distribution is uniform, the density is uniform. Okay. Secondly, about the center of gravity, if the gravitational field is uniform, center of gravity coincide with center of mass, and if the mass distribution also uniform, then center of gravity coincides with the geometric center of the regular shaped object. Okay. Okay, so the center of gravity of regular shape objects, something like a square sheet. or circular disc. Okay, so the center of gravity is at the geometric center. This is true only if, okay, the center of gravity of an object will be in their geometric center if and only if two things are satisfied. Okay, so first one is the gravitation field, the mass distribution is uniform. Mass distribution is uniform. In other words, I can say uniform density. Density is uniform. Uniform density. And second thing, uh, the gravitation field is uniform. Okay. So, by the way, as I told you in our syllabus, we discuss about objects in a uniform field, right? Even if you take this non-uniform field, now I'm living in Earth. Earth has non-uniform field because when we go higher and higher, the gravitation field strength decreases, right? But if you consider object like in size of 10 meter or uh, even 50 meter, 100 meter, now let's say this 100-meter length object, okay. So the gravitation field at here and here are approximately equal. Like for example, if I say here 9.802, here it will be 9.70799. So very small decimal change will be there. Okay. So therefore, we can still consider this as a uniform gravitation field. So nothing to worry. In our syllabus, we talk about fully uniform gravitation field. Therefore, the center of gravity will coincide with geometric center if the mass distribution is uniform. Okay. So here you note down this, the center of gravity is at geometric center. So then it has to be satisfy these two things. The mass distribution should be uniform, gravitation field should be uniform. Okay. So now, for example, if you consider a square, side A into A, that means length is A. So I'll draw a square here. So if I take a square, each side length A, okay. The center of gravity is at A divided by 2. So in x direction A divided by 2 and y direction A divided by 2. So it means here will be the center point. Okay. Okay, I'll give you the center of gravity of regular shaped objects. Okay. So you can write the topic center of gravity of regular shaped object. Also here you have to mention regular center. Okay, I'll give the topic center of gravity of regular shaped uniform object. Uniform objects. So after this, write down the topic. Center of gravity of regular shape uniform object. So uniform means the density is uniform. Okay, the mass distribution is uniform. Okay, so you can, yeah. So this is the resource book. I think I might have the English one also. වස්තුවක ගුරුත්ව කේන්ද්‍රයන් වූ එය මත සංප්‍රයුක්ත ගුරුත්ව බලය හෙවත් එහි බර ක්‍රියාත්මක වන ලක්ෂයයි. Resource book. Where did I? Where I have the resource in English as well later. Mhm. Okay, good. Okay, so you can note down this center of gravity of regular shaped bodies. Here you have to say uniform within bracket uniform density. Okay. Okay, I have got some messages. Okay, you can note down. You can. You can't see any changes in screen. Uh, okay, yeah. Yeah. Hold on. I check. I stop sharing. Share. Your screen sharing is paused. Okay. I hope you can see it now. Okay, so you can write down the first uniform rod. So if the length is L, its center of gravity will be at the midpoint. Okay, and uniform ring. So Okay, so here's the center of mass of a ring also at the center. Now, if you take an object, there is no any restriction, like the center of mass should be within the object. Now, if you take this ring, now its center of mass is not within the object, right? So it is in the space, the middle. Okay. You can write down. You can write uniform rod and draw this and these things. The center of mass in the ring is here, the same point. If the mass distribution is uniform, then it will coincide with the geometric center. If you take a circular shape, the geometric center is its center now. So the center of mass is here. Therefore, center of gravity also will be here. And third, you have a uniform circular disc. If you couldn't draw, don't worry. I will share this screenshots also. Okay. Or else you can take a screenshot. Okay. You can take a screenshot and then you can complete your drawings later. Uniform regular shape lamina. Lamina means thin sheet. For thin sheets, we call lamina. So center of gravity will be the intersection of two diagonals. And if you take a triangular lamina, how do you get the center of gravity? So say you have a triangular lamina. So you have to draw a line from the vertex to the midpoint of the opposite side. And from this vertex to the midpoint of the opposite side. And from this vertex, then if I draw these two correctly, then definitely this will go through the center intersection. Okay. And here you should know that if this is the center of gravity here, or the center of mass also will be the same point. Here, this length, this length ratio is 1 to 2. So this one length to this length 1 to 2. That means if this length is 2 centimeter, this will be 4 centimeter. If this is 5 centimeter, this will be 10 centimeter. The ratio is 1 to 2. Okay, so that is here. It will be the same for any type of triangle, like you can take isosceles or equilateral triangle or right angle triangle. So for any triangle, this is the method you find the center of gravity. Okay. and the center of gravity of uniform hollow cone. Now in physics, we only take the results, but those who are doing combined maths, you have a separate unit called center of gravity, which is I like the most in the this one in applied. In applied paper, the first question I'll take is center of gravity because it's very easy. It's just you have to do the integrate the density or the mass over the volume. So and this uniform color cone, uniform solid cone. In combined maths, you have to find all of this using integration. Guys, give me a second. Okay, uniform hollow sphere or solid sphere, the center of gravity will be at the center point, midpoint. So that's all. And there are only few things I need to discuss about the theory, and then we can do calculations. Okay, to find the center of gravity of irregular shapes, something like this. For example, if I have an object like no regular shape, okay, for this we can find the center of gravity in suspension method. That means you hang this from a particular point. Then we know if I hang this object, if I take an object and hang it from a center of hang it from a particular point. So then if I drop this, it will oscillate and comes to a stable position so that the tension and the gravity, the weight will be aligned, right? Finding anything to show. Mm. Okay, now for example, here I have this, but this is a definitely regular shape. So anyway, let's say if I hang this from here, so it remains stable because the center of gravity is also aligned along this line, because this you can see the midpoint, and if you draw the what do you call this diagonals, you go from the middle. So from this point the weight is acting, and then the tension, actually it's a friction here on my hand, and this one have friction, so that friction and the weight is aligned, so there is no movement. But if I hang it from here, if I pull from here, the friction is acting from here, and then gravity is here, there will be a movement. So it will, what happens? It will rotate, and due to this friction, this rotation, this energy is decreased, energy is wasting, so it loses kinetic energy, and also resistance is there. So if I drop this, what happens is it will oscillate, and it's a damping oscillation because there is energy loss. Then finally, again, it aligns with the center of gravity of this object, okay, which is here midpoint. So likewise, you can say if you have a regular shape object, you can hang it from three different places. First, if you hang from one particular point, then you can draw the line. So let's say if you hang this particular object which I draw in the screen, uh, sorry, give me a second. So its center of gravity will be vertically downward. So you can draw a line. So the center of gravity will be somewhere on this line. Okay. If I hang this and this is equilibrium configuration, I mean it's stable like this, then here the tension and the weight is downward from somewhere on this point. So therefore the weight, the center of gravity is somewhere on this line on the object. Okay, and then again what I can do is I can hang from somewhere here. So if I hang from here, then what happens? Uh, Assume now this is the downward, okay, because I can't draw the same picture again on the screen. So is the ground, and then this G is downward this side. Then it will balance in that direction. I mean, it is difficult from all else. Okay, I think I might be maybe possible for me to draw again. Yeah, hold on. I'll try. Can't rotate. Allah. There is no rotating option. So I take the same object and I wanted to rotate, but there is no option to rotate here. Okay, so now here I take this object and I have draw a line. Okay, so that line is from here to here. So this line will be here. And then next thing what I do is I take the same object and hang from different points somewhere here. So then let's say if I hang from here, then you can draw a line again because the tension will be here, and then you can find there is intersection point, that is the center of gravity. Okay, to confirm whether you have got the right correct point, if you have like to make it sure, what you can do is you can hang it from another third point. So if you hang from this particular point again, it should go from there. Okay, do you understand? Raise your hand if you understood, because I want to know whether you understood or not, because um, I didn't rotate the object, instead I changed the gravitational field. So therefore I'm not sure whether you have understood or not. So please let me know if you understood. I think only Hiroshi's raised the hand. What about Atika, Abhyushani, Zufar? Please let me know. Atika understood. Abhyushani, Zufar? Okay, let me explain again. All right, hold on. Give me a second, I'll be back soon. Okay, here piece of paper I cut into some irregular shape. Okay, right. So now let's say this is a. You can think this as a metal sheet, for example. Okay, and now I want to find the center of gravity of this object. For that, what I can do is first I hang it from here. So then if I hang from here, so it will. You can see now. Initially I'm holding like this, and then if I hold hang from here, what happens? Sorry, it's my fan. It's interrupting. Okay. So if I hang it from here, what happens? Here the tension and then here gravity, weight. So there will be a, if I from this point, if you consider there is a non-zero movement, there will be a moment of force. So therefore it will, what happens? It will swing. Okay. Due to the moment of force, it will actually here is a I have friction in my hand. That's why it's stopping. Okay. Otherwise, what happens? It will oscillate and then oscillate and finally comes to the equilibrium position. So when it's balanced like this, then you can draw a vertical line. Okay. So I draw a vertical line. Okay. So here's a vertical line. And then what I can do is again I want to hang it from another point. Okay. So then what happens now here? I'm forwarding from here and release my hand. So if I hang it from here, then again, now when I hang from here, what happens? Here the tension will be there. Tension, and then the weight at somewhere from this. It could be here, here, or here, or here, or here. Depends on the mass distribution. Somewhere on this line, the weight acts vertically downward, W. Okay. So I know now center of gravity will be somewhere on this line. Now what I do is I want to hold this from some other point and I release it. Then it will be balanced here. That means the center of gravity will be somewhere on this vertical line. Okay. Okay. So then this intersection point is the center of gravity. Okay. And to confirm whether you got the correct point, you can hang it from another third point. Then it should also go from this G. Okay. Did you understand? Abhushan, is it clear now? And Zufar? Okay. So that way you can find the center of gravity of any irregular shape. Okay. You can use this method for regular shaped object also. Okay. Give me a second. I'm sweating. All right. Okay. And then mathematical method. From here only we get the questions. Okay. If a body is made up of several small masses, M1, M2, M3, etc., located at position x1, y1, x2, y2, x3, y2, etc., in the coordinate of center of gravity, xc, y, c, g, given by, so x is sigma mi xi divided by sigma. This is actually the equation that we wrote for to find the center of mass. Okay, because here if you write, okay, so if I write the definition for center of gravity, So, to find the center of gravity, plumbing method, it is nothing, it's the same thing actually. Plumbing method means, those bars using that string and small weight, that thing, plumb line. We call that the plumb line, no? So it's a string and then the small weight will be there. These people who construction bars, they use to see whether it's vertical or so that it's simply a string and a weight. Okay. So instead of drawing the lines, you can use the string, and then with using the string, you can mark the line correctly. Okay. Both are more like the same thing. Suspension method and pump line method. Suspension is both more like the same thing. Here also you had to do the same thing only, like what I have explained here, to do the same thing, but now here instead of drawing the line, you first also you use the plumb line. So with the aid of plumb line, we can draw the line. Okay. All right. So the center of gravity, is actually it's come from the definition of moment of force. Okay. Now, how we calculate this is actually the center of mass. Okay, so the center of gravity, how do we write? The m1g, the weight times the distance x1 into x1 plus m2g. Okay, the moment of force is, we know that m1 g times, let's say, distance x1 plus m2g times x2 plus m3g times x3 plus dot dot dot. Let's say there are n number of particles are there, mn g times xn. Okay, so that one should divided by, okay, or else I explain. This is the total movement. Now let's say this is the mass of an object is there. Okay, so it made of small masses m1, m2, m3, m4, m5, m6, like a number of mass are there. Then you are taking the movement from an axis. That axis, it's your choice. You can choose, and you can choose the axis here. You can, if you want, you can choose the axis here, or else if you want, you can choose somewhere far. If you want, you can choose here. If you want, you can choose the axis here. If you want, choose the axis here, or if you want, you can choose the axis on the center of gravity. I mean, we don't know, but assuming we are taking from the center of gravity, and also you can do. Okay, so now let's say I'm taking the axis here. Then this is the mass m1, and then the distance x1, m2 distance x2, m3 distance x3. So in moment of force, we studied the net moment about a point due to every force, right? F1 times d, F2 times d, F3 times d is equals to the moment uh, made by the resultant of these forces from that same point. So the resultant of this, we know the resultant weight of all of this acts from the center of gravity, the definition of center of gravity, the point where it's all the weight is acting. So here capital Mg where capital M is equals to sigma, or else before writing the sigma notation, I write M1 plus M2 plus today my accrue like accrue. Okay, so here M is equals to M1 plus M2 plus M3 plus dot, dot, to Mn. Okay, so the total weight is from the center of gravity. So here I can write M1 plus M2 plus M3 plus dot plus Mn times G. So in the left hand side, G is common in all the terms. So you can take G out in the left hand side. So if you take then M1 x1 plus M2 x2 plus M3 x3 plus dot Mn xn is equals to here the total mass we can take. This is equals to sigma mi. So sigma mi, you add all the masses m1 to mn, I equals 1 to n. Okay, so sigma mi times g. So g in the right hand side and left hand side cancel. So here we get sigma into weight into the distance x bar. So into x bar. So weight into force into the distance. Let's say this distance is x bar. So therefore, here g and g cancel in the, so we get the equation. On the left hand side, we have sigma mi xi equals to sigma mi times x bar. So therefore, x bar is equals to sigma mi xi divided by sigma mi. So sigma mi is the total mass. If the total mass of the object is given, you can use that in the denominator. So we write the definition form sigma mi. Okay. Let me know whether you understood this. So therefore, the center of gravity is, we can take the x bar, and now if you find from x bar, you will find only this line, somewhere in this line. So if you want to relocate exactly, then you have to take the moment from another axis also. So here from somewhere like from this axis, you have to take the movement, then you can find the location of y. So by taking the x and y coordinate, you can find the exact location of g. Okay. In your syllabus in physics, by using this theory, you're supposed to find the center of gravity of only two-dimensional. You don't have three-dimension thing. So if you have three dimensions, then the only thing is you will get then z coordinate also. So zcg will be sigma mi zi over sigma mi. But we have only two-dimensional. Okay, one dimension and two dimension, maximum two dimensions. You don't have any in your syllabus. You don't have three dimensions. Okay. If there's anything you didn't understand, please let me know. Okay. So I hope everyone is clear with this. So after that, we can do some questions. Okay, we studied this earlier, those pictures. Applications of center of gravity, engineering and design. Stability of vehicle, bridges and tall building depends on their center of gravity. To make the stability more stable, we try to make the center of gravity as much as lower. Okay. There is during the World War, Second World War, Hitler, excuse me. Okay, so there is a story regarding the Hitler during the Second World War. Uh, when they, if I'm correct, yeah, during the Second World War, they wanted to create a car which can climb a large inclination. So that Hitler brought all the engineers in the country, and specifically, I think around 100 or something, I'm not sure the count, so 100 or 500 engineers in this project, and then they made able to create a car which can climb angle more than 70, something like that. Okay, so after succeed of that project, Hitler killed all the engineers who are involved in that, because he didn't want that knowledge sharing to other enemy countries. I'm not sure about this story, but this story I heard from one of my combined maths teacher when I was studying. Okay, so sports equipment like cricket bats. Yeah. The Taj Mahal also, you can see there is a beam kind of thing like in the bottom, so it's more dense. I mean, heavy at the bottom, so uh, it's more stable. He also killed all the designers. So is that story is true, right? I'm not 100% sure about it. Was one of the lecturer who told me, but yeah, he wouldn't be lying, right? So that might be true. Okay. Robotics and automation. Robotics are designed to have low center of gravity to ensure stability while moving. Everyday life example, balancing a spoon in finger, carrying heavy loads on the head, like in traditional markets, etc. Okay. And also, I can give you a good example of center of gravity is this one. In sea, there is a huge, what do you call, compartment that where we take this crude oil and all. I'm not getting the word. The word for that. I just search. Hmm. Let's put the keyword sea, crude oil, extraction. Yeah, this one. uh, drilling, these drilling machines. Okay, so here this drilling machine also, we use the properties of center of gravity. Some drilling machines are directly connected to the ground by these. Okay, and there is some other drilling machines which float actually. It floats and then we can use anchoring. Wait, I can. Okay, so these type of drilling machines, you can see these columns are huge tank. So this is actually float type. It's floating and anchoring to the ground. So these are not, yeah, these are not floating. Okay. Uh, okay, I'll show you. There's one YouTube video regarding showing the stability of this drilling machine with the concept of center of gravity. There's one video. Yeah, I wish search and share after the class. Okay, it's about the center of gravity of this drilling machine with uh, the stability of that. Explaining. All right. So before we move on to stability, we'll do some questions related to center of gravity. So now, for example, if you have a mass distribution, which we did in the last class, something like this. Uh, okay, so for example, if you have a mass distribution, here a mass, here a mass, and here a mass, and here a mass, and if you want to find the center of gravity, you can do the calculation similar to what we did in the last class in center of mass. Okay. Okay, we'll do some questions from center of gravity. I'll give you one question. Quickly find the center of gravity of this mass distribution. can mark the masses. Let's say the mass 1 kilogram. I just put the numbers. So each all in the units of kilogram. Is it for me difficult to write here? 1 kilogram. And let's keep another here 2 kilogram. Here 2 kilogram. 4 kilogram. Here 3 kilogram. And 1 kilogram. Okay, so find the center of gravity coordinates of center of gravity. So the center of gravity coordinates given by, let's say, x bar comma b bar, and h bar is, we know, is equals to sigma mi psi over sigma mi, and y bar is equals to sigma mi y bar sigma mi. Okay, let's see. So you want to find the coordinates of center of gravity. So here x bar we can find sigma in my inside. I'm starting from here. This is 2 kilogram. So 2 into the distance is 2 plus, and in the we have another 2 into 3 plus is no, and here we can't include this because from the y-axis the distance is 0. So these two don't make any movement about y-axis. And then this is 1 kilogram into minus 1, 1 into minus 1, and this minus 3 into 2 divided by total mass is 13. So 2 into 2 4, and here 6 10, 10 minus 1 9, 9 minus 6, 9 minus 6 3, 3 over 15. Am I correct? No, what is that? 2 into 2 and 2 into 3 and 1 into minus 1, 3 into 2 plus 3 into minus 2, it will be minus 3 into 2. Okay, so 2 into 2 4, 2 into 3 6, 4 and 6 10, 10 minus 1 9, 9 minus 6 3, 3 over 13. So here I haven't given the units, so you can leave it at that. Okay, if the units are given in meters, then you have to write here in meters, but since the units is not given, you can simply keep it as 3 over 13. And then y bar we can write, so above the y-axis, the 2 kilogram into 2, then 1 into 2, this 1 into 1. This one don't make any movement about the x-axis. This 4 into minus 1, minus 4 into 1, this minus 2 into 1. Whole thing divided by total mass is 13. 2 into 2 4, 4 and 2 6, 6 and 1 7, 7 minus 4 3, 3 minus 2 1, 1 over 13. Who has got the same answer? So therefore G equals 3 over 13, comma 1 over 14. So G is 3 over 13 is 0 point number. So there is plus in here 3 over 13, 1 over 13. Somewhere here will be the center. It's very close. So even smaller than 0.1. So somewhere here close to the origin, this G will be there. Okay. Very good. Okay. So this is very similar to what we have done in the finding center of mass. Because when you write this equation for as I did earlier, so taking the moments of weights, the G will cancel off both sides. So then you will get the same equation that we got for center of mass. Okay, and then let's do one more question. Yeah, see, there was a question in the source book. Maybe we can do that question. Okay, now here something like this wheel. Okay, now here it's made of three objects. One is ring shape, and then here two rods. Okay, now if you take this one center of gravity will be at the midpoint, and if you consider this rod, its center of gravity will be midpoint, and this one center of gravity will be midpoint. All three objects center of gravity midpoint, so center of gravity won't change. So therefore we no need to do any calculation and find the location of, you can easily identify the location of the center of gravity. And let's see how to find the center of gravity of such object here. Here it's made of two sheets. One is rectangle shape, the other one is triangular shape. So the rectangle shape, we know the center of gravity will be at their midpoint, where if you draw the diagonals, so at the intersection of the diagonals, the center of gravity of that will be there. And here you can see the triangular lamina. So in the triangular lamina, the center of gravity will be here. And if you make a object which combined of these two, then its center of gravity, guys, give me a second. Okay, so here we want to find the center of gravity of this combined object. We know if two forces are acting parallelly in one direction, the resultant will be somewhere within that region, right? We studied this in the moment of force. Find the line of action of the resultant, right? So if the two forces are acting in the same direction, the center of gravity will be, the resultant will be somewhere within that region, right? And if the two, let's say this two of this weight are same, like for example, I can show you here. Suppose here M1 is equals to M2, then the center of gravity will be the midpoint of the line joining G1 and G2. It will be the midpoint of G1 and G2 if M1 is equals to M2. Okay. Okay, so here we have two laminas. Let's try to find the x value. Okay, so here the question is you need to find the value of x. That means the location of the combined, the center of gravity of the combined object. Okay, so then what you can do is you can take the moment from this point. So if I'm doing this question, I will take the moment from G. Okay, So here I'll take the moment from the point G, clockwise movement. So if I consider the clockwise movement, so G, this M2G weight is making a clockwise movement, and this length we want to write. What is this length will be? How do I find this length? So this triangle 10 centimeter, 10 centimeter. So therefore this length will be length is here 10 and this is 10. So they have given. We want to, we should find this length here. 10 centimeter, 10 centimeter. Okay, so this length is there 16 centimeter. Okay, can do this. All right. So here I'm going to take the moment from point G in clockwise direction. So this M2G into the perpendicular distance. This distance I want to find. So that one I can find using this. This is 16 means this, this has and this bisects. This is 8 centimeter. So 10, 6 means this length will be 8 squared plus 6 squared is 10 squared, 6. So this length is 6. Okay, from here to here it will be 6 centimeter. So we know the center of gravity divides 1 to 2 ratio. If you take the triangle lamina, it divides 1 to 2 ratio. Therefore, I can find, let's say this point is M. So I want to find mg2. mg2 is 1 out of 3 of 6 centimeter. Because total 1 plus 2, 3. Out of that 1 is here into the total length is 6. 1 out of 3 of 6 centimeter is mg2. So therefore this length is 2 centimeter. Okay. This length is 2 centimeter. Therefore then I want to take this length, this small length. I'll zoom this entire thing. Okay. So here this length is 2 centimeter. Because this is 8 centimeter. So therefore this length will be 6 centimeter by the Pythagoras theorem. So therefore here the ratio is 1 to 2. So therefore this will be 2 centimeter. And this length is we want to write in terms of x. This is 20 means this will be 10 centimeter. Right? Because it will be the middle point, midpoint, 10 centimeter. So therefore this is 10, this is also 10 centimeter. So therefore this will be 10 minus x. So I again take the moment from G, then we have M2G times this length. This is 10 minus x, 10 minus x plus this length is 2. Okay, that makes clockwise movement, and G, this one, mass is making anti-clockwise. M1G times the distance is taken as x times x. This is equals to the moment made by the resultant. Resultant is the total mass m1 plus m2 g weight into the total weight, the moment made by the total weight of the combined object. And I'm taking from the center of gravity point, so the perpendicular distance will be 0. So therefore here I get m2g times 10 and 2 12 minus x is equals to minus term. If you take the other side, you get m1 gx. So now if you know the value of m1 and m2, you can put that and find the value of x here. Okay, is that clear? They have given the mass values. Okay, so here we have considered this both the lamina made of same material, same density will be there. Okay, so both the materials made of uh, both sheets, both lamina made of the same material, same density is there. So then you can find the mass M2. So you can find the mass of this M2 as M2 is equals to so here surface area, surface density, let's say sigma times area. The mass per unit area times the area is here 20 into 16. Okay, and then M1 you can find a triangle. So M1 is equals to the mass is sigma times half into base is 16 into height is 6. Okay, so then we can plug those values here. So here we have sigma into 20 into 16 into 12 minus x is equals to m1 is sigma into here g and g cancels, we can cut in this step. Okay, g and g cancels, so I'm not writing g here, and m1 is sigma into half into 16 into 6 into x. Okay, so here we can 16 and 16 can cancel, sigma and sigma can cancel. So 20 into 12 minus x equals here 3x. So 20 into 12 is 24, 240 minus 20x equals 3x. So 240 equals minus 20 this side, 23x. Therefore, x equals 240 divided by 23. Okay. So here it's a lamina, so it has a thin, it's a thin sheet. Therefore, the mass you can consider as mass is equals to mass per unit volume, the surface density times the area. Mass is we can take like this. Okay. Okay. So the important thing is you have to understand the concept, how to get this center of gravity and those things. 36 over 23 times by, yeah, 23, no, I got 36 over 23. Thirty-six over 23. What's wrong with this? 20 into 16. 20 into 16 times 12 minus x equals half into base is 16 into height is 6. And here 3x. Here 20 Minus 20x. I get a different answer. Okay, let's check what they have done. So they also taken the moment from center of gravity. So here the perpendicular distance is 0. Okay, m2g times g2. m2g times g2. So the distance is 12 minus x. Yeah, same thing I got. g1g. Okay, and then 20 into 16. Wait, hold on. Do this. We are taking the moment from g in the clockwise direction. So we have m2g. m2g into the perpendicular distance is this one. This length is 10 minus x. 10 minus x. Okay. And then this distance is actually this length is 6 centimeter. So 1 out of 3 into 6 means 2. So if you add that 2 here, the distance will be 12 minus x here. That's okay. I have taken the masses in different side. Yes. Okay. So I have found that my mistake was. Yeah. So here I have marked the masses differently. Okay. Here I had to take the mass of the triangle. I have taken the mass of the rectangle, and here it should be the mass of rectangle. I have taken the mass of the triangle. So that's what's wrong. So here then I can write m2 is 20, the mass of the triangle lamina. So which is half into base is 16 into height 6 into the distance 12 minus x is equals to m1, the mass of the rectangle, which is 20 into 16. This is the area, and then the sigma cancels, right? Times the x. Okay. So then 16 and 16 cancel. Here 6 divided by 2, 3. So 3 into 12 minus x equals 20x. Therefore, we get 36 is equals to 23x. The minus 3x comes to this side plus 3x. Therefore, x equals 36 over 23. Same answer. Okay. So here in this question, we add two different masses. Okay. So here we take one rectangle and then we add a triangle. So this one center of gravity here G1 and this one center of gravity G2, and then you can consider the movement of forces to find the center of gravity G. Okay, and also there are other type of question where, let's say you have a rectangle lamina, from that you cut the triangular part. Okay, so then you have to find the center of gravity of such object also. Now here the triangle lamina is added. Now if you triangle lamina is cut and take out, then center of gravity will be, now initially let's say it is, if you have only the this rectangle, the G1 will be here, and the triangular part G2 will be here. If you cut and remove this part, then we know the line of action of the resultant will be here to go in this side. It will in the same direction of the larger mass, and it goes a little bit to the out of these two. Okay, so such kind of question also there. We'll do one example from that. I will find and send you in the group. Okay, did you understand this? How to find center of gravity? I think I have some questions from center of gravity. I'll share you this sheet, these past paper questions from center of gravity. The center of gravity questions from every year. I'll share this also. Okay, only theory remaining to discuss about center of gravity is the stability. And also we want to discuss some more questions. The stability of center of gravity. So that part I will discuss in our next class. That is just 10 to 15 minutes not main discussion. The stability of a center of gravity. Stable equilibrium. What is stable equilibrium? What is unstable equilibrium? Neutral equilibrium. Okay, so with that, we'll conclude the today's class. If you have any questions, you can ask me. Yeah, that's all for today. Any questions? Okay then, so good night. Study well, take care.